Hello, everyone, and welcome to part 4 of Atlas's series of Fundamentals of Weathering webinars. My name is Oscar Cordo, and I'm going to be your presenter today. Today's topic is on weathering, testing, and basic standards. Let me first start off by thanking you all for attending, taking some time off from your busy schedules. As you'll note, I have my camera on. I'm just going to have it on for the first couple of slides, so you have an idea of who I am and the mess behind me. First slide that I'd like to talk to you about is our summary of who I am. My name is Oscar Cordo. I'm the Global Manager of Technical Standards, Trademarks, and Copyrights. I'm here for the U.S. and international territories. My of all the information on this page, the most relevant piece of information are my email address and the phone number. I want to stress to you that I want to encourage you, and please feel free to contact me at any time if you should have any questions, not only on this topic, but on any topic which is related to weathering. I'm here to help at any time. Please, I encourage you to contact me. Little bit about my formal position and what my responsibilities are. I'm responsible for coordinating all standards committee activities for the Atlas U.S. sales territories, but I also participate globally, and I also have global responsibility for Atlas's trademark and copyright management activities. I'm an active participating member of SAE, ASTM, AATCC, and AMA, or FGIA, as it's now known. My official roles within these committees currently serve as the chairman for ASTM Committee G3 on durability of materials, which writes some of the more popular ASTM basic weathering standards. Talk a little bit more about those in our presentation today. I also serve as the chairman of Committee G301 on joint weathering projects and past chairman of ASTM G309 on terminology for weathering. Internationally, I serve as a U.S. delegate to ISO TC61 on plastics, as well as a U.S. delegate to ISO TC38 on textiles, and I currently serve as the chairman for the U.S. delegation to ISO TC35 SC9 on coatings. Professionally, I have over 30 plus years of experience in all aspects of weathering and light fastness materials, which includes experience in all areas of weathering technologies for applications and different departments in our services laboratories. I have experiences on the application of weathering technologies on different materials, having past experiences, as I mentioned before, in both the areas of natural as well as the accelerated weathering laboratory. And my education includes an undergraduate degree in electrical engineering, as well as a postgraduate degree in management and computer information systems from Nova Southeastern University. So before we start, I'm going to talk a little bit about some of the housekeeping issues. Please note that everyone has been muted on this webinar, but at any time you can text me any of the questions by using the questions button on the lower right-hand side of your screen. Go to webinar control panel. We hope that this event is going to last approximately 1 hour. I expect to get through the presentation in about 50 to 55 minutes, reserving the last 5 minutes or so for questions. But if there are a lot of questions, I may extend it by a few minutes, and we'll judge it by ear. However, if I don't get to your question, these are being recorded. Now I'm going to follow up with a response for you to the registration email that you guys have provided. No need to worry about taking detailed notes. Some of these slides are pretty comprehensive, so don't worry about taking notes, because there's going to be a link sent to you after the presentation with to download a PDF copy of the slides, and this is going to be sent to you shortly after the webinar concludes. All participants who have a valid business email account will receive this link. I also want to stress to you that the download link has an expiration date. So as soon as you get the email, download the file as quickly as possible, because it will expire. And after the presentation, we're going to ask that you take a short survey. And this information allows us to fine tune our presentations to meet your specific needs. And finally, we'd like to encourage you to visit our online seminar calendar using the link which is shown at the end, to visit our LinkedIn landing page for some current information on our client ed online and hopefully soon to be in-person activities. So our fundamentals of weathering series of standards are independent seminars, but they fit together. As I mentioned today's presentation is going to take 55 minutes, talking primarily about the test method development basic standards. We're going to talk about what basic standards are and what application standards are. Some of the important environmental conditions which are talked about in the standards, a little bit about reference materials, and give some examples of some of these standards. The other series which we've already presented were the first one, which is factors of weathering, outdoor weathering, and laboratory weathering. And I strongly encourage you that if you didn't have a chance to participate in those, you can download those from our website or from our GoToWebinar landing page. And subsequently, we'll be providing 2 webinars on acceleration and correlation. Here's a slide of who Atlas is, who we are. I promise this is going to be the only bit of advertising or talking about who we are. We've got a lot of subject matter to talk about, but Atlas is the leading company globally in terms of history, size, and innovation in outdoor as well as laboratory weathering, testing equipment, and services. And we operate on these 4 primary cornerstones of our weathering business. First and foremost, on the left-hand, upper left-hand, we have our weathering instruments, where we pioneered the first textile light fastness instruments back in the early 1900s. And today we provide the broadest product lines in both laboratory weathering as well as corrosion test equipment. Our outdoor and laboratory weathering services pillar consists of our laboratories. And we have laboratories located throughout the world, the primary laboratories being here in the United States in subtropical environment in South Florida and desert environment in Phoenix, as well as our accelerated laboratory in the Chicago area. And we also have accelerated weathering laboratories in Germany. We also have outdoor sites in south of France as well as in India. The Atlas Custom Systems pillar, it designs and builds custom solar simulating lighting systems, especially for large-scale testing of environmental chambers. And finally, the client education consulting and standards pillar, where Atlas provides technical weathering consulting and client education, either online or in person. And in this pillar, we actively lead weathering standards development activities in key markets. This presentation today is a subset of this pillar, of this area in our business. Now, the first topic we're going to talk about today is, we'll briefly talk about the different types of standards and basic standards, what they are. First and foremost, we think of standardization, and we think of the standards we use, and some of them are rather new, but standardization in itself is rather old. You may ask yourself, how old is it? Well, it's nothing new. The ancient Egyptians standardized the dimensions used in the mud tiles used in the pyramids. And the Romans, they standardized the dimensions, the weight, and the identification method, which were used to manufacture the lead pipes, which were used in their aqueduct systems. If you look up standardization or standards in Wikipedia, you'll see that there are different descriptions of these devices and all that. But from the description, you'll see that the bore of the pipe that led from the public water supply to the public properties, as well as the width of the pipe. It specified the flow and the fees that were charged for these services. They also specified in their standards what happened if you tampered or if there was fraudulent use of the water supply. If you think of how you think of these examples, but modern days standardization, it's a little bit over 100 years old. The first examples of modern standards were ASTM standards, which were done in the late 1800s, primarily for the train industry. A standard, pardon me, a standard is defined by Webster's online dictionary as something which is established by authority, custom, or general consent as a model or an example, or something which is set up or established by authority as a rule for the measure of quantity, weight, extent, value, or quality. And this is a very, specific and general definition. However, another definition which clearly defines how we use standards in our industry, it is that it's an agreement or a way of communicating between two or more people or entities, such as two or more different companies or industry groups. Although we think of standards as documents, they can also be physical devices. For example, the standard meter stick is a physical standard which is located at for example, NIST and other national metrology laboratories. ISO, it defines a standard as a document which is established by consensus, and it's approved by a recognized body that provides for a common and repeated use. It provides rules, guidelines, or characteristics for activities or their results, and it's aimed at the achievement of the optimum degree of order in a given context. And it notes that it should be based on consolidated results in science, technology, and experience, and aimed at the promotion of optimum community benefits. So summarizing all of these definitions and putting it in the context of how we reference standards in our industry, a standard, it's basically a document which is established by mutual consent of mutual or multiple parties, that it's established by authority as a rule for the measure of quantity, weight, extent, value, or quality. And it should be, and I stress should be, because we see many examples of standards which aren't. They should be based on good science and data and aimed at the benefit of the general user community. So one may ask themselves, what is standardization and how is this task accomplished? Well, standards development means working alongside with your customers, regulatory bodies, competitors, and other stakeholders from around the world to debate technical issues, hopefully to share research data and to exchange knowledge. Standards development organizations, or SDOs, you'll hear me use that term throughout the presentation. And they ensure that everyone's voice is heard through provisions that all committees have by having bylaws, which are agreed upon by the participants, and they typically are vetted by a legal staff within that SDO. And fairness is ensured through a required balance of interest between producers, users, and general interest members, and through a consensual voting process that ensures due process. Although meeting discussions can sometimes and many times be very lively, meetings are, for the most part, structured and follow popular meeting guidelines such as Robert's Rules of Order. So reliable light fastness and weathering tests are the main goal for standards in weathering. And the intent is to develop standards that are both repeatable and reproducible, ensuring that the industry can use these methods to effectively market and sell their products with an acceptable level of confidence. To summarize all of that, the primary goal in using a standard is to minimize risk, is to minimize the risk of going to market with a specific product that you may have failure with. So the organizations that are responsible for writing standards are known as standards development organizations, or SDOs, as I mentioned before. And an SDO provides a forum for stakeholders to develop technical standards through committee structure and a standardized approval process. And they basically create, promote, and sell standards as a value-added service. And an SDO, it's primarily responsible for coordinating committee meetings, as well as providing resources, both human and logistical, to facilitate the standards development process. Want to stress to you that the typical SDO source of income are profits generated from the sale of the published standards and membership fees. So they have a vested interest in the quality of the standards that are developed. And here's a picture of a very few subset of different SDOs that we're involved with in weathering standards, but there are many more. The landscape in international standardization may appear to be complex, but it's actually very structured. The global direction is typically provided in this diagram that I have from the top down. It's global direction is provided, and it's linked through the UN through trade regulations through the United Nations. International standards development, such as ISO and IEC, are tasked to develop international standards. And in some instances, there's a cooperation and joint development of standards with regional organization such as with CEN and CENELEC. So you'll see that there's an interaction between the international activities in ISO, between the regional European activities in CEN, similarly between IEC and CENELEC for the electronics industry. So expertise is provided by participating nations through their respective national standardizations. For example, DIN in Germany, the BSI in the United Kingdom, or ANSI, which is the American National Standards Institute in the United States. In the US, the environment is a little bit more complex. The national standards body that represents the United States is ISO. In ISO is ANSI, but they have limited standards development themselves, and they serve primarily to coordinate standards activities at a national level. Thus, here in the United States, expertise is provided by individual SDOs for particular industries. For example, ASTM provides expertise to ISO for the USA for many of the weathering committees that we're participating in. And for example, for the textile industry, it's AATCC. So speaking of ASTM, a group of scientists and engineers led by a gentleman by the name of Charles Benjamin Dudley, they formed ASTM in 1898 to address the frequent rail breaks. As I mentioned before, it was developed primarily for the rail industry. And the group developed a standard to manufacture rails, originally called the American Society of Testing Materials. It became the American Society of Testing Materials before it changed its name to ASTM International in the early 2000s. And with its headquarters in Pennsylvania, they also now have offices in Belgium, Canada, China, Mexico, as well as in Washington, D.C. And in modern standardization, ASTM is considered to be one of the oldest SDOs developing standards. Expertise can also come from trade organizations, for example, SAE for the automotive industry, the VDA, and others. So complex, it appears complex, but everything pretty much funnels up to the top, where you have regional and trade organizations funneling their expertise up through the international market. So this slide shows a very concise list of industry committees that develop weathering standards. If you look at textile industry here in the United States, we have AATCCC, ATCC, or A squared as we sometimes call it. And in ASTM, the primary committees developing weathering standards are ASTM Committee G3, General Weathering Applications, DO1 for coatings, and ASTM D20 for plastics. And in ISO internationally, we have ISO TC35 for coatings, TC38 for textiles, and TC61 for plastics. And finally, I've listed SAE, which is a Society of Automotive Materials for automotive applications. I listed SAE, which published the popular SAE weathering standards. If some of you are familiar with the older J24, SAE J2412 and J2527 standards, these were standards developed by IFAI through SAE. And the automotive companies have reverted to developing their own standards and are now slowly transitioning to using primary SDOs like ASTM and ISO to disseminate their industry standards as opposed to SAE standards. Now we're talking. Now we'll talk a little bit about the different types of standards, which we classify as instrument-based standards, and in the next slide we'll talk about performance-based standards. And so, differing from performance-based standards, instrument-based standards, which are sometimes referred to as prescriptive standards, they contain specific descriptions of the equipment which is used in the standard, including the type, detailed drawings, manufacturer, contact information, and other information that gives precise guidance for performing the test. These methods, as opposed to performance-based standards, they're going to provide very good reproducibility if only one instrument type is specified. With this type of specification, settings and control parameters which are unique to specific instrument types are included in the standard, thus making these standards much easier for users to follow and to use. Although no longer as popular as performance-based standards because of international requirements to allow for competitive designs and not to prohibit the advent or the inclusion of potentially more advanced technologies. Instrument standards are still being used in some of the older standards, as well as individual company specifications that require a higher level of accuracy in the results, which are not attainable with performance-based standards. The nice thing about these standards is that although they don't give you many choices in instruments, they provide for very high levels of reproducibility. And as I mentioned before, the new trend in standardization is the development of performance-based standards. And if you compare both of these types, the performance-based standards concentrate on the purpose of the standard and do not contain detailed device or manufacturer descriptions for the testing equipment. They're going to allow the users to perform tests which are not dependent on specific equipment characteristics, since they're based on test performance. And they allow manufacturers to develop and improve devices without being constrained to a specific technology. The key or the most important factor in a performance-based standard is that you need to clearly and specifically define what the performance requirements are for the standard. If you don't define the performance requirements that you're looking for, you may introduce significant variability and lack of reproducibility in the test method. So in weathering, as I mentioned in the introductory, there's two different types of standards, two general classifications. We have basic standards and we have material or product specifications. In a basic standard, it includes guidance on general test requirements and provides the general exposure conditions, as well as providing specific guidance on the operation, the maintenance, and the upkeep of the actual weathering devices, or on performing the natural exposures outdoors. These are general in nature, and there are only a handful of basic standards that are commonly used. However, while there's only a few basic standards, there's many material product specifications, which in turn refer back to these basic standards for specific exposure guidance. The material standards, they provide guidance unique to a specific material or a product which is being tested. It provides guidance on sample preparation specifically for that application, the properties which are to be evaluated, whether or not a reference material is going to be used, and sometimes, not always, a test endpoint, hopefully with a pass-fail criteria in the specification, for example. So here are some of the examples of the more popular basic standards in weathering. And I've broken them up here primarily by international groups. We have the ISO standards, the ISO textile standard, basic standard for light fastness, general light fastness testing of interior materials. It's ISO 105 BO2. For plastics, we have the ISO 4892 series of standards and ISO 4892-2 specifically for using xenon arc devices for testing plastics. Similarly, for the coatings industry, we have ISO 16474-2, which is the xenon standards for coatings, or as ISO refers to it, paints and varnishes. And here in the US, in ASTM, we have the ASTM standards. And if you look at some of the examples that I've shown here, ASTM G7 gives guidance on performing direct outdoor natural weathering exposures. This is typically the guidance that's used in our weathering facilities in Phoenix and Miami. And similar to ISO 4892-2 and ISO 16474-2, we have ASTM G155, which is the xenon test, the ASTM xenon exposure standard. Current revisions of these most basic standards they're performance based. I want to stress to you that they only give general descriptions for the device and for the sensors which are used. We'll talk a little bit more about that in detail. This list is far from all inclusive, and the basic standards from other weathering devices such as for carbon arc and fluorescent UV, which I didn't list here, but there's basic standards for the different weathering technologies which are used in our industry. And one thing you should note is that the general current trend is to revise and develop basic standards as performance based. And finally, that these standards are living documents. For example, in ISO, each standard is reviewed every 5 years. Similarly, for ASTM, it's every 5 years. If a standard is not revised or reapproved in 8 years, it falls off the books. So these standards remain current. So we talked about the basic standards. Now we'll talk a little bit about the material or product specifications. And shown here are examples of material standards that reference some of the basic standards which we talked about before. Some of these standards, they may be unfamiliar to you. The first two primarily used by the building industry in Europe to perform weathering on two types of materials and products. The standard ASTM D7869, for example, was developed by a consortium, joint consortium between Ford, Honda, Boeing, as well as the suppliers and instrument manufacturers. Atlas and QLab were also involved in the development of this standard, and is becoming very popular due to the extensive research done supporting its development. And we'll talk about it specifically on the development and current trends in this standard at the end of our presentation today. And this material standard references ASTM G155. And similarly for plastics, we have ASTM D2565, which is a material specification used by the plastics industry primarily in the United States. Here we see the key variables we need to look for in weathering standards, more specifically laboratory accelerated standards. All standards, they typically include a title, a scope, normative references, terms and symbols, and abbreviations. And these are usually part of the standards template for a standard specified by the SDO. In laboratory weathering and light fastness standards, the requirement for the light source are usually specified. And this may include the light source, the spectral power distribution requirements, which will give you guidance on which lamp filters to use, as well as specs on sensors to measure the different parameters like irradiance, temperature, and humidity. the standard will also provide guidance on sample preparation, replicates to use, and if weathering reference materials should be used in the test. Weathering standards will also provide specifics on the test cycle, such as the length or the frequency of spray and light and dark cycles. Some standards, typically specifications, will also provide a test duration or minimum set of performance requirements. And finally, some standards also provide guidance on the evaluations of the specific material which is being tested, as well as guidance on the preparation for the test report. You can tell a lot of information just by looking at the standard's numerical designation or its primary title. In ISO standards, each standard has a latest publication year as a suffix. ISO standards may also have several prefixes. And the EN prefix specifies that the standard has been adopted by the European Union as a European standard. And individual countries may also adopt the standards as their own national standard. In the two examples which are shown here, the BS prefix indicates that the UK has adopted it as a national standard, and the DN prefix indicates adoption by Germany. The nomenclature used for the ASTM standards, it's a little bit simpler. The first suffix following the dash indicates the year of the latest revision. And many times when a standard is reviewed by the authoring committee, no technical revisions are made, and the standard is simply reapproved. In this case, the reapproval year is placed as a second suffix in the parentheses shown here. And this tells the user that the version is technically identical to the previous revision. Sorry about that. So key point, these are only two SDOs on, and all other standards sources may have their own nomenclature requirements, but a key point that I want you to take from this is that, and I mentioned this in one of the previous slides, is that the standards are living documents and that they're regularly reviewed to update the state of the art. That's one of the key focuses in standardization, is that they remain technically relevant, and they go a long way in making sure that the standards remain current. So weathering and light fastness standards are categorized in three primary categories, or buckets of, if you want to call them that. Weathering standards are often used for weathering of exterior applications, and this is this top category. And when you're looking at the parameters that are typically specified in weathering standards, you have outdoor daylight simulation. The heat, you have relatively normal temperatures or close to ambient temperatures, and humidity or moisture is applied in the form of rain or spray cycles due relative humidity. I'm not going to go into a lot of details and specific examples, but if you look at the different instruments which are specified for weathering tests, you have xenon arc tests, you have fluorescent UV, carbon arc, and as well as direct outdoor exposures. And the climates which are simulated are either moderate conditions, humid, or dry desert conditions. Here are some of the different applications and some of the example test methods. For light fastness, the light fastness bucket, we have group of standards which parameters are modified for indoor or interior applications. And when I say indoor or interior applications, I mean non-automotive. The parameters that are typically specified and controlled: radiation source, the light source is daylight behind window glass. Again, heat temperatures are normal temperatures, not very high temperatures. Humidity or moisture is applied in the form of relative humidity. It doesn't contain spray cycles. We're trying to simulate an indoor environment. The outdoor exposures are typically done behind window glass for these applications. And we have test methods for xenon arc as well as fluorescent UV and carbon arc. Mentioned before that it's for simulating an interior climate. And the different applications apparel industry, the furniture, packaging, paper. Typically, you have dry, light only cycles or light and dark cycles, no spray. And here's some of the example test methods. And finally, the third bucket, and this is where it's a little bit different than what we're accustomed to, is the category which we call hot light fastness. And this is for testing of materials for automotive interior applications. Difference between the second and the third categories is that the light source, although it's behind glass, or in some cases automotive glass, behind automotive glass, the primary difference is that the temperatures are much higher. That's why they're called hot light fastness test, simulating the automotive interior environment, which is typically at much higher and elevated temperatures than you would see in a typical indoor environment. For outdoor exposures, we have behind window glass, we have IPDP boxes, which are called IPDP because it's designed for instrument panels and door panels. We also have black box exposures. Primarily, the instrument types that are used are xenon arc and carbon arc. There are still some fluorescent UV standards still specified. Again, simulating the automotive interior environment, used for plastics, coatings, leather, and textiles. Typically dry and light cycles. And here are some examples of some of the more popular industry standards which contain hot light fastness cycles. I want to stress, or I want to state that I caveated each category, which these applications are most often used, because there are countless examples of standards applications that you would typically fit in one category, but use the conditions in another classifications. These are just general classifications or descriptions that we like to make, but in many cases it's not black or white. There's some applications which you would think were interior applications but are exposed in weathering applications. Here's a summary slide for the ISO basic standard for paints and for the paints and varnishes industry, the plastics industry, as well as the textile industry. And most applications almost universally refer to these basic standards. However, there are a few exceptions. There's some other basic standards for example, photovoltaics and for interior graphics and what have you. But for the most part, these are the basic standards which are used in our industry. And each industry has both standards using natural solar radiation as well as laboratory devices. You'll see that paint and varnishes has examples: natural solar radiation or outdoor weathering, and laboratory light sources, similar for plastics and textiles. For laboratory light sources, you'll see that there are standards for exposures using different types of radiation sources: xenon arc, fluorescent UV, and carbon arc. Xenon arc here in textiles, primarily the choice for textiles, but for coatings you also see that they have xenon, fluorescent, and carbon arc. One thing to note for those of you which are familiar with the ISO coating standards, the ISO 16474 series of standards, it has replaced the former ISO 11341 and ISO 11507 standards. And I also mentioned harmonization in this slide because many of the standards, more specifically using laboratory light sources, they have very similar standards across different applications. For example, the coatings, plastics and textile industries, the xenon arc standards are very similar. So if you look at, I've shown it in blue, the Part 2 and ISO B10. These standards are very similar, and they're harmonized in many ways. You'll see a little bit about that when we talk about the filter specifications. And similarly, between the paints and plastics industry, you have harmonized fluorescent UV standards. Here's a summary slide of the standards used for weathering light fastness of plastics or polymers. And I won't go into specific details because you reference specifics which may be of interest to you at your convenience. when you receive your copy. But the key point I'd like for you to get from this is that each industry will have options for different types of exposures in different devices or using natural solar radiation. Results may not be comparable, but you are given the options. And another point that I want to make is that some industries will also provide guidance on calibration and measurement of variables. For example, here you see ISO 9370, which is for calibration and measurement of solar or for the radiation sources. And we also see here that the plastics industry has given specific guidance for the reporting of evaluations in ISO 4582. So here we see examples of open backed exposures, talking a little bit about natural weathering exposures and what conditions to look for in natural weathering standards such as ISO 877-1, which is shown here. One of the primary things that you need to consider is the backing consideration. When you back an exposure, you have higher temperatures than unbacked exposures. There is no in an unbacked and a backed exposure, there is no convective cooling on the backside of the specimen, so the temperatures will be higher. Not all materials exposed to direct outdoor conditions of weather. Indirect or under glass weathering might be used for household materials like drapes or carpets, automotive interior materials. This type of testing was initially developed by AATCC or A-Squared, as I mentioned to you briefly before. But it's also been adopted by ASTM and ISO standards. And here's only a few examples of natural weathering. Some of the primary conditions you need to look for in these standards: the type of climate, the class of the climate, the types of exposure. When recording the environmental conditions, the standard will tell you to either measure total radiant exposure, UV radiant exposure, as well as other weather information such as relative humidity, time of wetness, wind speed. And it may also provide guidance on how to express your results and changes in properties, levels of exposure changes, stages, either by radiant exposure time, and finally climatic conditions. Here are some of the examples of natural outdoor weathering standards showing the popular exposure conditions. Here we see I mentioned the open backed exposure, where you have lower temperatures than if you were to use the backed exposures. And here are the underglass exposures for interior applications. Although they're all done outdoors, different applications, for example, coatings typically use unbacked exposures. You'll have some of the plastics or materials which are typically exposed backed in their end use applications, exposed in this configuration, which will produce different results. And finally, your underglass exposures for interior applications, as well as automotive interior. Here we see a cross section of the solar concentrating devices, which is specified in ASTM G90 or ISO 877-3. And the samples are mounted facing down in this area, which we call the target board in the drawing. And sunlight, which is natural solar radiation, it reflects off these 10 mirrors onto the target board. And in this way, significant acceleration can be achieved using natural solar radiation or natural sunlight. And it provides for a very realistic simulation for many materials. Here we see some of the exposures I mentioned. These devices, they track the sun. So the mirrors are actually facing the light source, and here we see the light reflecting off the mirrors onto the target board. And in some cases, we have the facilities for spraying to simulate different cycles for automotive, exterior applications, simulating soft fluid exposures, what have you. Now we'll start talking a little bit about the accelerated or laboratory accelerated devices and the standards, what variables they specify in their standards so that you can accurately and reproducibly run your test. The key variables that you need to focus on for laboratory accelerated weathering, first and foremost, is the variables for monitoring, controlling all test variables, for controlling irradiance, your spectral power distribution, which tells you which filters to use, what your sample surface temperature, your reference surface temperatures should be, your test chamber temperature, your ambient temperature, and your relative humidity. When I talk about sample surface temperatures, most devices don't measure or don't have the facilities to measure the sample surface temperature to use those temperatures to control the devices. So they'll typically control a reference temperature, either a black or white. And we'll talk about a little bit about that in an upcoming slide. The next key variables that you should look at is a cycle, whether it's a dry only cycle or whether you have a spray cycle, and whether you're utilizing light only cycles or light and dark cycles. The standards also provide guidance on calibration, how frequently you should calibrate, and the design and the frequency at which different variables should be measured, and the systems that should be utilized to control these temperatures or relative humidity or other variables. And finally, the cooling mechanism, whether ambient air or cooling aggregate should be used. Here's I mentioned spectral irradiance and spectral power distribution. Here's an example of how spectral power distribution is defined in a standard, and it provides this standard, which is ISO 4892-2. It provides upper and lower limits in the different regions. Relative spectral portion is normalized between 300 and 400 nanometers. First in red, in the red nomenclature, we see the requirements for ISO 4892, and which is for plastics. And here we see the requirements for 4892-3, which is not for xenon, but for fluorescent UV devices. One thing I want to stress to you, and this is just one example of one standard and how they represent the requirements, but different standards represent these requirements in different ways. And because they can be confusing, we recommend to simply consult with your instrument manufacturer for guidance on the specific selection of filters or the light source to meet the standards requirements. It's many times very, very confusing. So which filter should I use? This is one of our most common questions. The answer, as I mentioned in the previous slide, is often defined by the specification in the standard. And the table in this slide is one example of the minimum and maximum requirements as a specific wavelength band. And this table just so happens to be for daylight simulation. Some standards, they're going to specify by a particular type of filter, filter types such as borosilicate inner and outer, or borosilicate soda lime for interior applications. While others, instead of telling you which specific filters to use, they're going to give you this specifications in tabular format or graphical format, so you can select your filters, leaving the how you get these, the simulation of that spectrum up to the manufacturer. I'm going to briefly touch upon type 1 and type 2 now, but more detail in the next slide, where you now have type 1 and type 2 daylight filters. For those of you that are used to the traditional daylight and window glass filters, now there's type 1 and type 2 daylight filters. So I mentioned in the previous slide that we have the daylight filter classification, and I wanted to point out that due to the development of newer filter systems that represent the solar cut-on much better than traditional factors, the basic standards in ASTM and ISO are revising their daylight filter classifications, type 1 and type 2 classifications. The type 2 filters include the broader traditional specifications, which encompass the commonly used daylight filters, which we're accustomed to using. For those of you using Atlas instruments, these are the Boro for the Atlas CI instruments. However, the new Type 1 filter classification, it now refines the solar cut-on requirements to a much closer representation of natural solar radiation. And the new classification includes the new right light filters, which were jointly developed by Atlas, Ford, and the filter manufacturer. And although the traditional Boro filters were good enough for some materials, if you look at the spectral power distribution in short wavelength region, the traditional Boro is shown here in red, and the increased short wavelength UV produced erroneous results for some materials. And the new bright light filter technology represents the state of the art in filter design, and it's now being used in weathering standards development. Represents the state of the art. So although the irradiance is specified in different wavelengths region, it's the same overall intensity in the instrument. The different regions and wavelengths which are provided to accommodate instruments using different sensor technologies or from different manufacturers. So if you look at standards, they'll provide, for example, for daylight, they'll provide values wideband, broadband, or narrowband. What we mean by broadband is 300 to 400, wideband 300 to 800 nanometers, and narrowband either at 340 nanometers or 420 nanometers. So I mentioned before that you can't directly measure sample temperature. So what we do in our industry is we measure reference temperature, either a black panel or a black standard temperature. And the different technologies which are used in weathering standards are either black standard sensors or what's sometimes called insulated black panel sensors, where you have a black coated stainless steel plate with insulated backing, PVDF insulation behind the actual behind the actual black coating, and you have a housing for electronics in the back. If you look at them face to face, a black standard does not have a probe on the surface, but it's insulated on the backside. The black panel sensor, sometimes called an uninsulated black panel, simply has a black coating. The backside is open to the airflow, and you have a sensor on the face. These are used for characterizing the maximum temperatures under solar heat or solar radiation load. Similarly, sometimes white-coated sensors are used to measure the minimum temperatures, and the manufacturing, the specifics onto the construction of these sensors is described in the basic standards in ISO 4892-1 and ISO 474-1, ISO ASTM G179 for outdoor black panels, and an ASTM G151 through 155. So as I noted in the previous slide, you have these two different types, black panel and black standard. But the black panel and black standard, if you place them in the same machine at the same time, you're going to report different values, simply because one's insulated and one isn't. And here we see a graphical representation how the same conditions in test results in the conditions result in different black standard and black panel temperatures at different irradiance levels. One thing I want to note is that at lower irradiance levels, the difference is lower, but as you increase the intensity and you increase the heat load, that difference between at higher temperatures, you're going to see a bigger difference between black standard and black panel. So at different temperature ranges, for example, if you have a black panel of 60 degrees, your black standard will only be a couple of degrees higher, whereas at 100 degrees C, it could be up to 10 degrees C. So differences are magnified at different temperature levels. So we've collected, and now we can look at some of the basic test cycles. And one of the most used weathering cycles, as I mentioned before, is ISO 4892-2. And if you look at the first bucket, we're talking about weathering. Here are the conditions which are provided for weathering of materials. We have cycle number 1, where you have the irradiance, both broadband and narrowband. And in cycle number 1, you have black standard temperature, as well as a chamber temperature and a relative humidity specification. And similarly, for light fastness testing, you have different irradiance levels. These are using obviously different filters, using window glass filters, different irradiance set point at 420 nanometers instead of 340 nanometer control. And the temperatures are shown, which I mentioned before, are lower than your hot light fastness options, which is method or cycle number 3, which has a continuously dry cycle, again using window glass filters, but if you note, the temperature is higher at 100 plus or minus 3. One thing I want to stress to you is that the cycles number 1, 2, and 3 specify black standard, but similarly, there are other cycles for black panel control in 4892-2. These are just typical cycles which are used in industry, and these cycles are harmonized with ISO 16474-2 for coatings, as well as ISO 105B10 for textiles. So here we see cycles 4, 5, and 6, where instead of having a black standard specification, I mentioned before that there's similar cycles 4, 5, and 6. We have weathering, light fastness, and hot light fastness, but instead of black standard, we now have a black panel specification. Similarly, for fluorescent UV instruments for different applications, we have different light sources. They're all fluorescent, but the light sources are the UVA 340 lamps with a peak at 340 nanometers. For interior applications, we have the UVA 351 lamps, which are for simulating daylight behind window glass. And then you have what we call extended UV with a peak at 313 nanometers. Sometimes unrealistic exposures, but very severe exposures for materials with sensitivity in the short wavelength UV region. And as I mentioned several slides ago, the plastics industry also gives guidance on sample evaluation. ISO 4582 instructs users on relevant evaluations for polymers after being exposed in a weathering or light fastness test. And it gives guidance on determination of changes in color and appearance attributes, determination of mechanical properties, changes in mechanical properties, how to express the results, the required precision, how the test report is to look, and the required accuracy. Weathering reference materials and some of the examples which are used in some of the standards. First and foremost, one of the more popular ones especially for the textiles, we call blue wools. ISO and AATCC have similar scales with materials which are with the lower numerical ratings. For example, ISO number 1 fades rather quickly. ISO number 8 is more light fast resistance. It takes longer to fade. For the automotive industry, and one of the more popular reference materials used in material analysis, polystyrene chips, which yellow as they degrade. BASF has their own material which they developed. When exposed to a specific set of requirements, the material will show cracking. It's difficult to see in this slide, but material will show cracking after a specified exposure level. And finally, another option, which is sometimes uses the OR-wet or orange weathering exposure testing coating, manufactured originally developed by EMPA, and it fades when exposed to a specific set of conditions. Now I'm going to briefly, since we're running short on time, I'm going to briefly run through our weathering standards, some examples of weathering standards, give you an idea of what's available. First and foremost, natural exposures. Typically, the test will specify benchmark exposures. Some of the benchmark exposures, subtropical exposures, which is a benchmark climate. It's a standard reference location for automotive coatings, and as well as architectural paints and coatings, which in these environments you have high relative humidity, high levels of time of wetness, high levels of UV radiation, and fairly warm consistently throughout the year. Typically, these exposures are located at the southern tip of Florida and Homestead, southwest of Miami. I mentioned the solar concentrating exposures, and these types of exposures are specified in ISO 877-3, SAE J1961, or ASTM G90. The nice thing about these standards is that you can achieve pretty high levels of high levels of acceleration utilizing natural irradiance. Very realistic solar spectrum. It's the actual solar spectrum, and it has the ability for nighttime wetting cycles or no spray cycles throughout the day. Some of the limitations because of this is that you also reflect infrared energy, so some of the materials may get too hot using the traditional exposures. Now there are new options in our other webinars. For example, the one on outdoor weathering, we show you different options for reducing your temperatures, for increasing irradiances. The testing suite available with these types of exposures has grown dramatically over the years. Looking at testing of light fastness of textiles, the general procedures for textile testing, they're exposed to either natural or simulated solar radiation, partially covered by a mask, and the exposure duration is according to a fixed level of time, radiant exposure, or based on the degradation which is observed in a reference material. Evaluations are typically according to color change, fading, differences between an unexposed or an exposed area, and visually they're rated according to a grayscale. Two of the more popular xenon arc textile standards are ISO 105 BO2 and AATCC test method 16.3. And although they serve the same purpose, the conditions are different. So I want to stress to you that the results aren't necessarily comparable, and comparable results can't be assured. There are differences in the spectrum, temperature, and humidity requirements, and some of the differences are shown in the red highlighted text. ISO 105 BL6 is the primary international standard for hot light fastness testing of automotive interior products, primarily textiles. And this basic standard serves as the basis for many automotive OEM standards. And here you can see 4 of the primary cycles which are summarized. Conditions number 3 are predominantly the most popular cycle, and in condition number, if in any of the test methods, there are different options on how to determine the test endpoint. 4 different methods. First method is by determining the color change in the specimen. The second method is to determine the color change in a reference spectrum, such as blue wool. Method number 3 is to determine the endpoint by aging test when the sample reaches a certain endpoint. And finally, method number 4 is to expose the material to a fixed amount of radiant energy, either kilojoules or megajoules. As I mentioned before, conditions number 3 is the most popular, and here's a summary of the test conditions. I'm not going to run through them in much detail. You can reference them. But if you look at which is the most popular test method in ISO 105 BL6, it's condition number 3. And for condition number 3, the endpoint is determined when ISO blue wool number 6, it fades to a grayscale rating of 3 on the ISO grayscale shown below here. And this equates to approximately a delta E of 4.3 plus or minus 0.3 CIE lab units. And this requirement is specified both in ISO 105 BO6 as well as in the German automotive specification VDA 75202. For window profiles, in Europe, one of the more popular test methods is EN 513 or EN 12608. Key thing I want to note with this slide is that this group is primarily concerned with sample temperature. And in machines, you can only control either the black reference temperature, either BST, or your air temperature, chamber temperature, which is your ambient temperature. But if you look at the typical specimen temperatures, they usually fall between your BST, your black standard temperature, and what we call a WST, or white standard temperature. So these test methods, they specify a range of white standard temperature, but machines can't control white standard temperature, so you have to adjust your chamber temperature accordingly until you get your white standard in this range. So in this way, you're better able to duplicate sample temperatures from test to test. And for weathering of wood coatings, one of the more popular test methods is this EN test method, where they specify fluorescent UV exposure. One of the things I want to stress to you here is that many different committees, although they're trying to do what the industry accepts, they may not be doing what the state of the art is. And there's recognized flaws in using fluorescent UV devices for testing color change, for example. So there's ongoing development to further refine the options available for the wood industry to get a more realistic and reproducible test. And when you look at, we'll start talking a little bit about automotive testing. First and foremost, I want to give you a brief background on the history of it. And for over 20 years, SAE J1960, which is now J2527, was used by the automotive industry as the de facto standard for testing automotive exterior materials. It was specified by the Detroit Big Three and Tier 1 suppliers. It was originally developed in the mid-1980s, primarily by General Motors. J1960 was originally developed in 1989, and it specified what we call extended UV filters. For those of you using Atlas CI instruments, these are the quartz inner borosilicate type S outer filters. However, in the late 1990s, Ford recognized that the extended UV filters provided erroneous results, or the conditions were too severe for many materials. So they started specifying daylight filters, or the boro filters, for their tests. And in 2004, SAE J2527 replaced J1960. It was the same basic set of conditions, but it was a performance-based standard versus an instrument-based standard, which J1960 only specified Atlas equipment. Now, one of the key things that I want to note here is that you have the use of spray cycles and light cycles, and you'll note afterwards that this is a key thing, a key deterrent in getting good correlation. Fixed irradiance level, which at the time we thought of was a high irradiance level, but in fact it was a low irradiance level. So this test method, although for many years was very popular, it really was not the state of the art. Now, in order for me to start talking about the importance of the right light filters and the importance of getting the filters right, I need to talk a little bit about photochemistry. I'm not going to talk too much about photochemistry today because this is one of the primary topics in our upcoming webinar on correlation, which is our sixth in our series of fundamentals of weathering. But however, to really show the importance of getting the light right, briefly going to talk about spectral sensitivity. Now, if you look at spectral sensitivity in a very simplistic form, the spectral sensitivity as the wavelength decreases, wavelength is on the x-axis here, as the wavelength decreases, a material's spectral sensitivity increases. Okay, and it's shown, for example, for this specific material in this black curve. Now, you also have the spectral power distribution of the light source which is being used. And here we show the blue, which is the spectral power distribution of natural sunlight. Just so happens that this spectral sensitivity is of human skin, and where the spectral sensitivity and the light source, where these two graphs interchange, or they intersect, the resultant area is what we call the activation spectrum. And this is the relative energy that serves to break the bonds or to degrade a material. So if you look at this fixed amount, is you have the intersection between natural daylight and this material's spectral sensitivity, you'll see that there's this fixed amount. However, if you use this light source, and this light source represents the extended UV filters that I was specifying for the SAE J2527 and J1960 exposures, you look at this intersection is much higher than this. So you have much more a higher activation energy affecting and degrading materials. So the key focus is to get a light source which accurately simulates the the spectral power distribution of natural sunlight. Very crude description. We talk about it in much more in depth in our other presentations, but there's a keen interaction between spectral sensitivity and spectral power distribution, which affects how well you're able to duplicate your exposures in an accelerated exposure. So, thus, to improve the testing of automotive coatings, consortium, which included Ford, Honda, BASF, Bayer, as well as the instrument manufacturers, they researched the testing environment and the unique processes of coating degradation in natural exposures. And after over 12 years of work, they helped develop the ASTM D7869. And to summarize this test method, xenon arc light source water exposure test with enhanced water exposure for transportation coatings, it was developed especially for coatings which are sensitive to photochemical degradation weathering, and the test cycle was designed to produce this cyclic exposure to moisture. And it was found during the development that existing standards did not reproduce these factors realistically. So the purpose of DA7869 was to reproduce realistically the degradation effects, both macro and microscopic degradation mechanisms observed in South Florida for coatings, specifically for automotive and eventually aerospace coatings. And the approach was to take a realistic simulation of the primary weathering factors. And it allows only filters which fall under the daylight type 1 category, as I mentioned before. So looking at the development of the new filter specification differences, if you look at natural daylight, which is shown in the black squiggly line, as well as and how it compares to the traditional Boro filters, which is the red, you see that there's no close match. Even worse, you see the extended UV filters and the differences here. But if you look at the right light, it falls right on, almost right on top of natural daylight in the important solar cut-on region. So the daylight filters the type Boro were an improvement, but still allowed short wavelength UV exposures. So the new filter system represents the state-of-the-art spectral UV match. So they were able to develop a filter, but there was still some differences being observed in the exposures. And why were these differences being observed? Well, it was because the effects on moisture and weathering. And the importance of moisture is that it serves as a plastification effort where it reduces modulus. It induces swelling because it induces stresses due to the differential stresses observed during the swelling process. You see blistering of the coatings because of moisture intrusion, loss of adhesion. Water serves as a mass transport agent, and it also serves as a mass loss, removal of film degradation from surface due to erosion. So water does play a critical role. And because of this, they developed a complex cycle. Here's a summary of this cycle, and to summarize, I'm not going to go into the details of the cycle. ASTM, for those of you interested, ASTM D7869 has an appendix which actually explains each of these step numbers and why they were developed. But the key points to remember is that they provided longer dark spray cycles to achieve moisture uptake levels for the coatings to achieve saturation. They provided multiple irradiance levels to simulate your outdoor conditions. That's what happens in real life. You have high levels during the peak, but morning and afternoon you have lower levels. As I mentioned before, you don't have any light or spray together. This was done in the SAE J2527, but it typically doesn't rain in max sunshine conditions. And you have some interspersed light and dark subcycles to simulate thermal shocks effects during natural exposures. And here we see the different cycles shown graphically, where the portions of the graph shown in blue are designed to maximize deep water penetration, promoting losses or showing failures in adhesion, blistering, and diffusion effects. And the areas shown in black are your cyclic, are shown to induce your cyclic stresses, which are to induce cracking, as well as surface erosion, which will be shown in changes in gloss. And finally, the areas, the different irradiance levels, which induce the different photo-oxidation rates. Now, in terms of degradation and correlation, the primary problem was that we were seeing some false positives on some false positives using traditional J2527 exposures. You were having materials passing J2527, which were failing in real-time exposures. And this were primarily seen in adhesion loss. Here you see this X scribe, no adhesion loss in J2527, but in real time you did have adhesion loss. With this new protocol, you're now able to effectively get the same simulation. And this is just one of the examples. We have other webinars specifically on automotive exterior coatings, which highlight and truly show the differences in these exposures. I mentioned that Boeing was part of the consortium, and there's a fundamental difference between the coating systems which are used for aerospace applications. Typically, automotive organization or automotive companies, they use multi-coat systems, base coat, clear coat systems, whereas the aerospace coatings are monocoat. But surprisingly, the primary concern is erosion loss in aerospace coatings, and shown by changes in gloss. And if you see here, there was no differentiation shown in using J2527, but in traditional South Florida exposures, you saw these changes or this differentiation between the different materials. And using the new protocol, you're now able to induce the same or replicate the same type of results that you see in South Florida. So also a very portable method, not only for automotive coatings, but for aerospace coatings as well. So here we reached the close to the end of our presentation, and we'll begin to summarize our what we presented today. Well, what is a good weathering standard, or what are the requirements for a good weathering standard? The goal is to provide a realistic simulation of materials' natural degradation behavior. Thus, careful consideration should be given to the selection of the climatic parameters. Material-specific properties should be evaluated. The description and limitations of the test devices should be specified to include the type of test instrument and the test instrument setup, which tells you which filter system, the type of surface temperature sensor, either black standard or black panel, the type of radiometer, either narrow, wide, or broadband, the type of specimen holder, either backed or unbacked. Also, the description and limitations of the test settings should be specified to include irradiance, surface and air and chamber air temperatures, relative humidity, spray time, pardon me, which would include time of wetness or the amount of water, and finally the equalizing time for the dynamic parameters. Now, with each limitation, pardon me, which each of these limitations, you reduce the risk of inconsistent or variable weathering results. And this is why, as I mentioned before, instrument-based standards were typically more precise, because there was less variability because of one instrument design. However, in performance-based standards, they widen the application. They can provide more variable results if the performance is not clearly defined. Finally, a good weathering standard will give guidance on reporting of equipment variables and device performance. And finally, variations, as I mentioned before, variations are unavoidable. But if the required reporting requirements in the standards, they will facilitate users in determining the sources of variability in their test results. So, in summary, standards in weathering are designed to provide repeatable and reproducible test results. We have both instrument-based as well as performance-based standards. Each have their own advantages and disadvantages. Weathering standards exist for natural and laboratory weathering and light fastest testing. We have basic as well as application-based standards specifically for materials, for specific materials. And some of these standards also provide guidance on sample preparation, evaluation, and instrument requirements. And finally, modern weathering standards development is more and more based on understanding and simulation of realistic degradation processes, as we saw in the development of ASTM D7869. So with that, this concludes our presentation today. I mentioned that this was part 4. The next portion is part 5, which is on acceleration, which includes descriptions on acceleration factors, time compression, intensification, and finally correlation, which I briefly talked about today. These independent seminars fit together. As I mentioned before, you're going to be sent a copy of the presentation. You'll be able to download your presentations if you have any questions. I see that we have one question. It says, for accelerated weathering of different polymers like polyethylene, polystyrene, polypropylene, which fluorescent lamps like UVA or UVB is suitable? For polymers in general, all the different lamps are allowed. If you look at ISO 4892-3, which is specifically for polymers, it will give you some guidance specifically for polymers on which lamps to select for the different applications. It's actually a pretty useful tool in developing specific set of requirements for your product. And that was the only question that was submitted throughout the presentation. But if any of you have any other questions, please feel free to send me your questions. I also want to highlight this summary slide that we'll have at the end, which gives you links to our recorded seminars, as well as our weathering blog and our LinkedIn page, weather summaries, which summarize the different conditions in our different laboratories. This can all be found on our website. So I hope you enjoyed today's seminar and hope you learned something useful for your work about your materials weathering standards. Thank you all for taking some time. I apologize for going over. It was a pretty comprehensive subject. But thank you so much for your patience, your attendance, and have a good day. Goodbye.